All right, let's see. Yeah, your written test is still being processed right now, but I should be able to return back to you very soon. So I'm gonna bring the paper, if not Thursday, Tuesday for sure next week, because it's gonna be your last class. I'll try Thursday because we also need to scan also the paper, because there will be a regrading procedure given to you. You can definitely submit some regrading requests if you got any concern. So we also need to scan the paper. So I'll just need to coordinate with Shanru, the TA, to do this. Anyway, I'll reach out to you about the idea. And then I'll bring the paper, and then you can take a look. I also bring you the answer as well. So you can also take a look at the answer, which might be useful for your exam study. All right, so your exam has been already confirmed. That's something I mentioned last time. And there will be some makeup and also exam study lecture altogether about bottom-up parsing. I'm going to release it hopefully tomorrow. It's already processed. I just need to post it also together with the notes. That's something you can definitely take the time to study before the actual exam day. You do have more than 2 weeks to actually do this. Okay, just follow that at your own pace and then get it done. And then, so there's a top-down parsing algorithm that we spoke about last time, the tracing exercise. So you can see the lecture site, you can see under exercises, the link is already there, right? Just in case you're not aware. So please take a look, and then I think that one also is going to help you do the tracing for the top-down parsing algorithm. So another thing that's also going to help would be the assignment number 3, which I released yesterday. So let me just show you here. All right, so assignment number 3, that one is really just about top-down parsing. So given what we covered in the last lecture, last Tuesday, just about the pseudocode and do some tracing, if you do the exercise, you will be ready to actually tackle this problem here. There will be some like a boundary cases we might touch into about backtracking, things like that. But those are the things that you will actually need to discover anyway when you're developing the code. But anyway, assignment 3, you should be ready to start doing it. I pushed the deadline just to the almost like 1 or 2 days before the exam. So just it's participation-based grading. Just make sure you do as much as possible. It's also going to help you understand about the algorithm itself for top-down parsing. So you can also make sure you submit before the due dates to claim your credits. Okay? Questions?
Would you say that you should watch the top-down parsing walkthrough video and then do assignment 3 and then watch the makeup video?
Okay, so yeah, I think that definitely, the sequence you mentioned definitely makes sense. I would say before you do assignment number 3, it definitely helps to really get a little bit more idea about how the top-down parsing works. Yes, I would suggest do it. Maybe just review the lecture notes about what we said about why the left recursive grammar is actually going to cause the algorithm not to terminate, even though we assume the input that's going to be supplied to your assignment number 3 algorithm would be right recursive. I think there's an explicit assumption about it. You don't really have to implement anything to remove the left recursion, but we'll talk about how to remove the left recursion today. Okay, that will be the idea. Anyway, so watch this video here as you suggested, and then do assignment number 3 along the way. And then, so this one will be something in parallel. Yeah, the makeup lecture. Yes? Yes, you'll be allowed to, yes. Yeah, it's going to be your work. So the reason is just for formality, just before I return the hard copy to everybody, I just need to scan the copy. Yeah, so when you actually submit any regrading request, we can just look at the scan copy. Yeah. Mm-hmm. I'll try to see if Shamru can actually get a scan done before Thursday. I just need to coordinate with him. But if no, the latest time, definitely Tuesday. But I'll try to make it earlier so you guys can know about the look at what you did, and also the standard answer and your marks as well. Okay.
Is today's lecture relevant to assignment 3 as well? Or
today is not directly relevant. That's something we assume for assignment number 3. Okay. All right, guys, any other questions? Okay. Yeah, so I think, of course, as you look at the grading scheme, the biggest thing will be for the exam. So I would say, please just plan your time to actually study everything that's going to be covered, and then, yes, you should be fine. Okay. All right, let's do a quick recap. So today, I just want to have cover 2 things. Number 1, how can we remove left recursion? Number 2, how can we remove some null production? So these are the 2 things. Okay, so, and then we'll see how long it's gonna take. Okay, hopefully not too long. Oh, guys, also by the way, so the project report template has been released. If you got questions or concern, you can let me know. You can talk to me after class or maybe during the office hour, but it's gonna be the report format we will expect your team to actually deliver when you make your final submission. I will also give you the exact PDF instruction about what you should really submit, but there should be no surprise. The final format is going to be quite similar and also consistent with the previous 2 milestones. You guys already got feedback from Shanru when you met with him, but if you want any additional feedback, you can feel free to reach out to me. Okay, so we can also talk about it. Okay, so let's now do a very quick recap from last time. So last time we basically started talking about, so we are trying to automate the discovery of derivation. So being able to do it manually is good. It's really good for our understanding, but in reality, no one is going to do the derivation by hands because the program, the input to your compiler is going to be very substantial, cannot be very small like Hello World program. So you really have to know how to do the derivation automatically. So meaning that like assignment number 3. But luckily, the kind of program you are implementing for assignment number 3, it is something that will be generated by Antler 4. So it's really based on your grammar, they can generate some parser directly. But I think for your kind of skill and also completeness for your understanding, it's good for you to also try to implement it by yourself. There are many specifics of the programming that's really nice to really do the assignment here and try to sharpen them. Okay, so that's something I would suggest you really spend some time, along the way. You're studying for the exam and also get prepared for your projects, many things in parallel. All right, so that's the ingredients about discovering the derivation. We have some input grammar and also we have some string. So the idea would be to build a parse tree at the end. Of course, to be more precise, either you would say it's an error, the string does not really conform. It's not derivable from the grammar. There'll be a like a syntax error, or you can actually build a tree. And the way you build a tree is going to be either top-down, which we talk about in the class, or it can be bottom-up, which you will study as a make-out lecture, an exam study lecture. Okay, so we talk about top-down versus bottom-up, right? We're going to talk more about top-down today, right? You basically just keep, it's a bit like a depth-first search. So you're trying to, once you have the start variable, you keep choosing the leftmost variable or leftmost branch that has not been completed yet, and keep going until you're done with it, and then you go back or backtrack to whatever rule that's not really being used or whatever expression that has not been produced yet. So you just keep going this process. And this process, abstractly speaking, is very easy to say. I just say in one sentence. You got to keep trying different paths about using the production rule. But to see exactly how to implement this, that's why we got assignment number 3 for you. You can see the assignment number 3 specification. It does give you some hints as well. It's quite a nice assignment, challenging, but at the same time, it's more like a participation grading. So just do your best attempt to really understand as much as you can. All right. And then we went through this algorithm over here. Okay, let's just take a quick look. Right, just at a high level. You can definitely refer to the recording for the precise detail. So what we're really given is a sequence of, you can think about a sequence of tokens or sequence of characters, to read one by one. And then what we have is input is actually a context-free grammar and also the string. And output is going to be syntax error if the parse tree cannot be built, or it's going to return the root of some parse tree. Okay? And this is simply the initialization stage. So we're going to have the root, the focus, and also the word. That's the current word we are trying to use to expand the tree. And also we got something called trace, just a stack, basically, right? And also one thing you may want to think about is in the pseudocode, we did say something to push null value in the beginning. In your particular implementation for assignment 3, that's something you may want to consider. But I wouldn't think you can just directly get rid of it without modifying the logic over here. So look into it, right? You may want to think to yourself, if you really don't like this line here, you may have to change your implementation a bit to adapt to it. All right, that's some comments for you. And also, while true over here, it is simply just the way the pseudocode was developed. If you also don't like this possibility of infinite loop, you can also modify the condition, right? Once you go to assignment number 3, you can do whatever adaptation you like from this pseudocode. All right, so we basically got case number 1, case number 2, case number 3, and case number 4. We got all these 4 cases. We'll talk about the backtrack a little bit later, but what we did last time was the focus can either be a variable or the focus could be matching the word that we are matching the word that we're currently processing. So especially for this case, right? So if you think about the tracing example we did, so we start with the expression, which is the start variable. And that will be the root and the focus at the same time. And then from expression, we know that it can produce either 1 expression plus term or 2 term. So we go one by one in the order, right? So we go for number 1 here, and then we got expression plus term. So now at this level here, we keep track from scratch again. So here, this leftmost variable here is expression. Again, for expression, it can be expression plus term or term. It's a different level of keeping track of what we have used already, right? Just remember, in your assignment number 3, when you are trying to keep track of the production rule, every time you're trying to go to a new level of the tree, you got to start over again. So you may have to keep making some copy of the rules, but that's something I'll left to you to implement, okay? Of course, you can feel free to use any Java library as you wish. Yeah.
Is this what you were mentioning, the leftmost derivation results in an infinite loop? So in the assignment, it just implicitly assumes the rightmost derivation?
Yes. No. Okay, I see exactly what you mean. Yeah. Okay. So I'll get there. Yes, I'm going to clarify that. So from this tracing here, as we did last time, so this one apparently is going to result in infinite loop. It's never going to terminate. So the root of the problem is the top-down parsing pseudocode. The logic is we're automating leftmost derivation. If you're automating leftmost derivation, but you're given some left recursive grammar, you can see expression right here is left recursive. That if that's what you have, you're going to run into infinite. The algorithm is not going to terminate, right? Like an infinite loop, basically. So there are 2 ways to fix it. Either you change this guy here to be discovering the rightmost derivation, but that's not what we're doing here. It's potentially yes, but that's not what we're doing for this assignment or in this course. We still keep the logic here to discover using the leftmost derivation. So what we change is the input over here. So in the assignment, you can assume that the input grammar you are passed to test your code is not going to contain any left recursion, something we can assume, okay? But in the lecture, we're going to talk about if you somehow want to make your program more general or more robust. In that way, you will have to add 1 extra pre-processing step. Any grammar you're taking for your program, you have to remove the left recursion, if any. But for the current assignment number 3, you don't need to. Okay, just something to keep in mind for your context. All right. All right, so for your assignment number 3, you definitely can assume you don't really get any grammar with a left recursion like this. You can assume that's not the case. But after today's lecture, you should really know if you're given such left recursive grammar, how are you supposed to remove the left recursion before you can get it processed, right? That's really the other end of the story we're trying to cover in the lecture. All right, so what about left recursion? So there are 2 kinds of left recursion. Direct one, you can see expression and appearing right away as a leftmost variable in the production. Right? If you got at least 1 occurrence or 1 production like this, the grammar is said to be left recursive. That's the direct one. Another way to really have a left recursion is indirect. In that way, you basically have a cycle among the dependency graph of the variables. You can see here we got A to B, B to C, and then C to A back. So there's a cycle there. If there's a cycle here, that's also considered as left recursive. So the algorithm we're going to go over today is the single algorithm is actually going to remove both the direct and indirect recursion. So as I actually go over with you the algorithm, I'll first of all try to go over with you line by line, just to make some annotation, just something for you to keep in mind. and you will see that there will be different phases of the algorithm. And phase number 1 will be to remove the indirect left recursion. And phase number 2 will be to remove the direct recursion. That's something you will see. I just want to give you some look ahead. Okay? So once we go over the algorithm, I'm going to do 2 examples together with you today. And then there will be some additional example will be exercises. I'll also give you some solution hints as well later. So that's something just for you to exercise. And that'll be for the left recursion, right? So at least you know how to remove it at a conceptual level. But if you want to implement it, given the conceptual understanding, you should also be able to implement it as well. All right. Okay, and then, so this is the important exercise. You guys will need to maybe give a try first before you actually look at the video, if necessary, to see how it can be traced. Okay, I'll leave that to you. And there's another one here, right? That one there will be followed in a very similar way, but that one you can also try as exercise. All right. All right, so today we're going to talk about left recursion. Okay, how to remove it, basically, because left recursion is going to cause your top-down parsing algorithm not to terminate. So we want to know how to remove it. Okay, let's look at the algorithm. So let me just, before I go over line by line, let's have a very quick overview. Okay, so the algorithm is going to take some input grammar, context-free grammar. All right, and the grammar has we have no assumption about the whether or not the grammar is left recursive, right recursive, or whatever. So if there's no left recursion here, we just got nothing to do, which is okay. If we do have any occurrence of left recursion, either direct or indirect, we're going to remove it. Okay, so that's the grammar here. It's completely assumptionless, no assumption about the input grammar. Oh, and then we also make some additional assumption. There's no epsilon production. Epsilon production simply means a variable produces epsilon string. Right? That's something I also talk about as well. Somehow, in this particular algorithm, as we actually go through, there is certain occasion where we might somehow introduce epsilon production somehow internally. But I will also show you a way how you can remove the epsilon production just to make the algorithm complete. Right? So, but for now, just to say the input does not have any epsilon production. I'll say a little bit more about this later. All right, so the output is just going to be another grammar, G prime, which may be just the same as G, in which case we know that there's no left recursion to remove. Right? All right, the procedure there is going to be a double. Okay, I'll talk about exactly what I really meant by impose an order. Because this part over here, imposing an order, is more like an arbitrary. It really depends on how you organize the input grammar. Okay? And then once we impose the order, we actually basically got a nested loop. It's like a quadratic algorithm, right? Like an n square algorithm. It's also the loop pattern here is very similar to maybe what you did in the first year course, like a 1022, when you first learned about like a nested loop. So that should be the familiar structure. But I'll try to maybe trace in a way that's higher level, just easier for you to see what we are really doing. Yep, I'll get there. All right, just notice that here we didn't say, okay, here 1 to n, and also we didn't say 1 to n again. We said 1 until I minus 1. And the I here is the dummy variable, or the loop counter for the outer loop. Right? I'm pretty sure you have seen this before, but we're going to see exactly how this pattern here can be useful for our purpose. And we got 2 phases over here. So phase number 1, okay, I will go to the detail later. So phase number 1 is completely within this nested, the inner loop. This part here is actually going to remove the indirect left recursion. We'll see exactly how. Okay, so the pseudocode over here uses lots of symbols over here just for pattern matching. So I will try to explain to you, first of all, conceptually how the symbols can be visualized and understood, and then we'll see concrete examples to see how we can instantiate these symbols. We'll do one step at a time. But just to remember, in order to remove the indirect left recursion, it's actually within the inner loop. And then the second phase, within the you can see this one, indentation kind of suggests. So this is the third phase over here. So this one here is within just the outer loop over here. All right? So that one there is actually going to, so this part here. So this is phase number 2. That one there is going to remove the direct left recursion. All right? So or we just try to remove the indirect and also remove the direct. Okay. One look ahead, also for you. We'll see that in one of the exercises we're going to do together. Interestingly, when we try to remove the indirect left recursion over here, it might be possible we unfortunately introduce some left recursion that's direct, which is not good, right? However, what's going to be followed in the phase number 2, we will be able to remove that direct left recursion right away. So overall, it's not going to cause any issue. All right? So that's something you will see as well in that exercise we're going to do together. All right? We'll see. Okay. All right. So here, yeah, this is simply some looping variants, which you guys maybe learned in 3101, right? You can take a look at the looping variant over here. Looping variant simply means there's certain Boolean condition that should be maintained true throughout each iteration. So maybe I'll leave this maybe looping variant bullet point just right over here. You can look at that. Once we do some tracing together, you can appreciate a little bit more about looping variant. When I recap the lecture on Thursday, I can revisit this looping variant so you can see a little bit more. Right? But you can take a look maybe after the lecture today. For now, you don't need to worry too much because you don't even know how the algorithm is supposed to work, right? So that's something we'll do first. Okay, so that's about some very quick overview. So let's now try to do some annotation here, okay? And then we'll do examples, okay? So first of all, you can see that when we talk about null production, right here, null production, and I can make a reminder right away. So when we say, oh, epsilon or null production, or epsilon production, okay, epsilon production, so it is of the form, if I have some variable, I say variable produces epsilon, okay? Very easy to define. And then, all right, so we assume there's no epsilon production and we got some input a grammar and output another grammar. Okay, we're gonna remove the indirect and direct. And let's look at this line here. Impose an order. This is something a little bit arbitrary to how you would like to proceed. Imposing order simply means we want to do this removal of the left recursion systematically. As long as you can follow the system according to the order you decide, you'll be fine. Okay? So for example, let's say this. Let's say this is the grammar we are given, right? Input grammar. So we got 1, 2, and 3. We got 3 variables. What's the most obvious way? What's one possible way that you can impose an order? I can say 1, 2, and 3. That's it. If you like, you can also say 1, 2, and 3. Nothing wrong with that. But today, we're going to do the exercise by following 1, 2, and 3. That's what we're going to do in class. However, if you just out of your curiosity, you may decide to try a different order. Let's say 1, 2, and 3. If you go with this particular order and you still follow the algorithm, it's still going to work. So impose an order is just to make sure you're doing things consistently. Exactly what that order is to start with doesn't really matter. All right, so that's something I want to also mention. Right? I'll put the order down again, maybe a little bit later. Okay. So for this part here, implementation-wise, you're just going to store the variables into some linear collection. So you're just going to store all the variables in a linear collection. Could be a list or could be an array. Better be not something that's non-linear. For example, if you store that in a tree, yeah, I don't think you can really impose an order unless you want to make it like a search tree, but it's overkill. Linear collection should be okay. All right. So that will be something we'll start with when we do the tracing, right? We'll just go for the most intuitive visual order. And then we have this nested loop structure over here. Okay, so you can see over here. Okay, so this is a nested loop. Okay. And you just want to notice that we got n here, and here we got I minus 1, and the I there simply correspond to the I right here, right? So the two loop counters somehow are related to each other. They are not exactly independent. But of course, if you based on your knowledge on 2011 or 2101 data structure, the algorithm will still be quadratic, even though it may not be exactly n times n. It might just be, well, it will still end up being n squared. Okay, just a aside. Okay. All right, so let's now talk about phase number 1, phase number 2. Okay, give you a little bit idea. I want to start with, let's say, phase number 1. So think about this part over here is really phase number 1. And then you can see for this phase number 1, it's completely within the inner loop. All right. On the other hand, you can see that this part over here, this for loop, right? You can see it's indented the same as the inner loop. So that means this is within just the outer loop, right? That's some important details to really attend to, right? So this will be phase number 2, right? And you got to be in this particular order. All right, let's now take a look at phase number 1 here. So we're going to do some replacement right here. Okay. First of all, this one here is supposed to eliminate indirect left recursion. You know what? I'll just save a little bit writing for myself. I'll say LR for left recursion. Okay, that's left recursion. On the other hand, this part over here, okay, I'll just try not to really compromise any of the symbols here. And this part right here is going to eliminate direct left recursions. All right, so they got different purposes, okay? Let's now try to see how we can understand this one here, all right? Looks a bit complicated, but for this kind of like a symbolic illustration about what the algorithm is supposed to do, we'll just try to make it very general. So all you got to do when you see the concrete example is to do some pattern matching, okay? I'll show you what I mean, okay? So here, so it's an if condition. We say that if there is at least one occurrence of this guy over here, in that way we should do some replacement. If there is no such no occurrence of this pattern here, then we don't do anything. All right. So let's now look at exactly what this condition is. Right. Let's look a little bit more closely. Right. I'll make it a little bit bigger. Okay. So first of all, you can see that we got AI. AI here simply means some variable. And this variable here corresponds to the current index that we are looking at. Okay, just notice that it has some correspondence. And if the current variable we are looking at actually produces another variable followed by something. And notice that here we got I here and we got J over here. So this tells us we are saying that if the current variable produces another variable, but not itself. Because if the current variable simply produces itself, it's a direct left recursion, which is not supposed to be handled at this stage. It's supposed to handle in the second phase. All right? So what we have is, you can see that AJ over here, okay, I can write down for you. So you can think about this part over here, this one here, and this one. They're supposed to be two different variables, distinct variables. Okay, so AI produces another variable followed by whatever. So whatever that's going to be to the right of that different variable, just call it gamma. All right, if this is a production rule, and so you got to be another part is also true. It's a conjunction. This AJ here produces any of the alternative. Okay, this is like a general way of saying AJ might only produce some string, or it might produce different alternative, as many as you like. So it's a very general way of pattern matching, right? So this could be maybe one part over here. or it could be another part all the way to n parts. All right? Recap. In order to preemptively, okay, so let's say eliminates, so we are trying to do this preemptively. Meaning that, so we're just trying to do all the replacements so that it's guaranteed at the end. There's no indirect, there's no cycle among the variable dependency. Okay? So let's talk about this one here. Let me see if there's anything else to say. Oh, just one more thing. And you can think about this guy here. The gamma here is simply just arbitrary string. Arbitrary mix of terminals and non-terminals, whatever you like. All right, if this condition is satisfied, we're going to do some replacement. The replacement is going to happen like this. What we identified was AI produces AI gamma, right? Sorry. What we identified was AI produces AJ and then gamma, exactly this. It's going to be replaced by the following rule. It's still going to be AI, the same. Okay, let me just highlight it. It's still going to be AI right here. But now AJ itself is going to be replaced by delta 1, delta 2, all the way to delta n. And the gamma here stay the same, stay the same, and stay the same. Let me say that once more. This used to be what can be derived from AI. But we try to preemptively eliminate the indirect left recursion. What we do is, this AJ part is going to be replaced by all the possible derivation or production by AJ according to some rule that we can identify. So that's why we see delta 1, delta 2, all the way to delta n. And whatever that goes, that follows the original AJ, they will still be here. We're not compromising any of the original rule. Okay, let me highlight it. So you still got the delta 1, delta 2, all the way to delta n. And the gamma that we have over here is still there. The gamma here and here. Very abstract, I agree, but once we see the concrete example, it's not too bad. We're just going to do some replacement as we go. So the individual replacement is not difficult, as long as we just do some practice, but to really do it in a systematic way. That's why the very first step about imposing an order on the variable is so important. Also, you got to follow that consistently. We'll get there. All right, that's about phase number 1. And phase number 2. So for some particular I variable, right, we're still looking at AI, right? You can see we got, let me just use a different color. Right? If we got AI here and AI here, right? Before we say AI and AJ, they are different variables because they have different indices in the order. But now we got AI and AI. Obviously, there's a direct left recursion, like expression produces expression plus something, right? So you got AI repeating itself as the leftmost variable on the right-hand side. And followed by a certain alpha, you may have some other alternative beta over here, all right? So alpha here is whatever that follows the recursion. And beta is just whatever other alternative you have for that particular variable. All right? And if that's a production rule, that means we got some work to do. Okay? So what we do is, so this is the interesting part that we need to dive a little bit further. Okay? I need to explain to you why replacing this production rule, obviously that's left recursive. How can we replace it by something else that, number 1, eliminates the left recursion. Number 2, semantically, it produces the same set of strings. Right? It's got to be both correct and also right recursive, basically. All right, let me write it down, and then we'll talk about this one. This one is a little bit tricky, but it's not too bad. So this one here, criteria, is going to be, number 1, correct. Number 2, left recursion removed. All right, and the way I'm going to show to you about this left recursion being correct, I'm just using, I don't really do any formal proof, but I think just by manipulating the symbol a little bit, you will see very clearly how it can be justified. We'll take a look at that. Okay, let's now take a look. Let me start with this one here, okay? This one here. So what I have is, I got AI produces itself followed by some alpha. Alpha is arbitrary mix of the terminals and non-terminal. A little bit like the gamma here. A little bit like, I just choose a different symbol so we don't really get confused. So it will be either this or beta. Okay? We'll put a justification somewhere. I'll put a justification here in just one moment. Okay? I'll just put a box over here. Right? We're going to talk about it. But before that, let me also write down what the replacement should be. Okay? So this will be some justification. I'll get there in just one moment. Okay? So we're going to replace this by right here. Okay? So this one here is left recursive. Oh, sorry. So this one here is left recursive. Which we know is not good. It's going to cause the top-down parsing algorithm to not to terminate. What we want to replace it with is something right here. This is something that's going to be shown to be right recursive. Okay, right here. And I'm going to put it out just in just one moment. And this is something that's going to be shown as right recursive. Okay, let me first of all write it down. Okay, you can simply say I'm just copying whatever expression is here. Okay, it's going to be AI. Still, AI is there, right? Here's the AI here and AI here. That one we don't change. But now I'm just going to say beta right here. I'm going to choose the beta here. All right, beta and then AI prime. It's a new variable we're going to introduce. Okay. Of course, since we're doing this exercise on paper, we're saying prime is valid, part of the, is a valid character as part of the name, right? So that's something we assume. And then AI prime produces, and we say alpha. You can see the alpha comes from the alpha right here, okay? And then we say AI prime. Okay, let me make it more obvious for you. So you can see that AI is still there, but you also introduce a new variable called AI prime. And you can see AI prime here, AI prime here. So obviously, this one tells you that it's right recursive, right? Now we got to justify. Sure, going from here to here, apparently you're going from some production rule that's left recursive and remove all the left recursion. But why is that correct? That's the thing, right? So now the way to justify is to really unfold the production rule right here to see what the pattern is. And then we can justify that. The pattern that can be unfolded from this rule over here is just the same as this one. All right, let's see. Okay. So you can see that we got two cases. Either we got a base case, either we can say AI can produce beta directly, okay? So case number one. So we got AI, and that one there can simply produces beta, right? Just one occurrence of beta, okay? And let's talk about the more recursive case. So let's say if we say AI, and then we say that one produces AI alpha, right? I choose this rule instead, right? AI produces AI alpha, all right? And then I can also choose to replace AI here by another AI alpha, right? I can also go further. This one here can be replaced by another AI alpha. But if you like, I can say this AI here is replaced by AI alpha right here, right? Just more obvious to you, okay? And then, so we can, and after this, of course, this can go on forever if you like. It can go for an unlimited number of unfoldings if you like. But let's say if now we decide to replace AI just by the base case beta. So that's what we can do. So we can say now it can be beta, alpha, alpha, right? So you can think about the AI here is simply replaced by beta. What does that tell us? That tells us this input pattern here that we identify right here has the unfolding that goes like we can have either a single beta or we can have just one single beta followed by as many alpha as we like, but at least one. Okay? That's kind of the pattern. Right? You can maybe verify yourself to make sure you're convinced about this pattern here. And once we are convinced about this pattern here is can just be generated no more, no less by this right recursive version. If you think about it, right? So you can see here AI, and then we can just get a beta. So this beta here comes at front. That corresponds to either beta here or the beta here, right? Comes at front. That part is okay. And then if you like, you can think about the beta over here really correspond to either the beta just by itself and also the beta right here. Right? So that part just partially justified. And then it can be this particular beta can be followed by as many alpha as you like, including zero occurrence of alpha, right? Because this will be as if there's no occurrence of alpha. That's really covered by the AI prime here. So you can see AI prime here. We're just going to say alpha over here, and then AI prime, right? As many as you like. Okay? Good? Question?
Going back to phase one.
Yeah.
Are you basically just combining all the rules of AI with the rules of AJ and getting rid of AJ completely?
You mean phase number one?
Yeah.
Yes, eventually, yes. We want to just kind of keep replacing the definition for each variable.
So
That,
we're basically folding away.
Yeah, in folding away, yes. Because you're trying to folding away, you somehow just eliminate. Folding away, you might result in some left, yeah, okay, good. So phase number one, over here. Phase number one here, you basically keep folding. Well, unfolding actually, not really folding. You keep substituting by the definition of the variable. But there's a catch. By doing phase number one, you might introduce direct left recursion. Because if there's a cycle there, implicitly, by keep replacing, you might still run into that cycle eventually. That's something we'll see. But that's okay. As long as the phase number two is going to take that newly introduced cycle and then do something about it. That's something we'll see. Okay, good. And guys, I just realized I got a very terrible typo here because this should be a possibility of epsilon, right? Because here we say that it can be followed by as many alpha as we like, including no alpha, right? So this epsilon here, I forgot to put it, right? My bad. So this one here should be, I'll put it here. AI prime, alpha AI prime, or epsilon. Okay, this is important because here we are saying that we can really do as many alpha as we like, including no alpha. All right? Because eventually you also want to terminate the case as well. Okay? So it's a very, in some ways, more like an informal, well, I would say semi-formal justification. We're just trying to basically study the pattern of string that's going to be generated by this left recursive version of production. And then we're arguing that this one here is just going to generate exactly the same pattern. So we're good. Okay? So this one justify about whenever you see any direct left recursion, which may be already existing in the input here, or it might be something that's introduced by the previous phase number 1. Either way, you just remove it. All right? So that's why the order is actually important, right? You basically do phase number 1, which might produce some additional left recursion, and doing phase number 2. Okay? Question?
If we were to just add all of the step-by-step
Yeah.
from AI alpha alpha, then we would go to beta AI prime alpha alpha, right?
So, okay, you're talking about this grammar here?
Using that rule, but
Mhm.
with the blue above, in the last step. when
Oh,
we're-
okay, so are you talking about the pink one or the orange one? Which one are you talking about?
The bottom one,
You mean the orange one here?
yeah.
This one here. What about it?
Oh, I see the top one.
First of all, are you convinced maybe the top one here can somehow produce this pattern here? Either we have a single beta here, followed by no alpha, or we can have a single beta here followed by at least one alpha, at least one.
I think I
Yeah,
understand.
yeah, okay. But if you like, if you want to put in like a regular expression, right? I'll put informal, okay? It's basically like a beta followed by alpha, and then we'll put a star over here. Okay, regular expression, which means you can have 0 or more occurrences of alpha. All right, and that's exactly what this will produce. And the epsilon here is actually very important. Okay, and one thing to note as well, as you can see, we assume input has no epsilon production. But now we are introducing epsilon production. That's okay, don't worry. We're also going to learn about how to eliminate epsilon production as well. Okay. Yeah. All right, it's a very quick, well, I wouldn't say quick, it's more like a detailed walkthrough about how this algorithm is supposed to be understood. Why don't we take a short break by taking attendance? After the break, we can actually do tracing quickly of 2 exercises. All right? All right. So before the break, we spoke about this algorithm over here, about how you can remove the left recursion over here, right? Right here. So what we do now is to see how we can apply this algorithm. So let me just give you some overall picture. So we're going to do 1A together in class today. And that one there is about removing something that's directly left recursive. Of course, in the actual exam, I may not actually give you this comment about this grammar is actually directly left recursive. That's something you got to judge anyway. So I would say every time you give me some grammar, you can maybe look at the grammar yourself to have some idea about why it is left recursive, either directly, indirectly, or both. So you have some idea about what's really involved to really remove the left recursion. So we'll do 1A together. And then 1B over here will be exercise for you. I'll just write it down here. Okay. So this will be exercise for you. I can write better. Okay, this will be exercise for you. And then we're going to see 2A. So this would be something that's indirectly left recursive. So we wouldn't really do an example where it's both directly and also indirectly left recursive. That's something, as long as you follow the principle and try to apply the algorithm faithfully, it should be done in a similar way. But we're going to, just for simplicity in the lecture, so we just do either it's only directly left recursive, or it's only indirectly left recursive, either way. Okay, we're also going to do 2A in class today, right? And then for 2B, oh, I'm so sorry. Okay, I'll just write it down. So for 2B is also exercise for you. And for 2C, slightly more challenging, that's also exercise for you. So we do 1A and 2A. So 1B, 2B, 2C will be exercises for you. All right, good. So let's see how far we can go. We've got about 25 minutes. Should be okay. Yeah. Okay. Okay, let's do this one here. But for now, just pretend you didn't see this comment here. Okay, we're just going to apply the algorithm faithfully. Okay, and when you're doing this, let's sort out the first problem. So we said that we have to impose an order on the variables, right? So let's now do the following. Let's just do the most obvious way, right? Doesn't need to be the only way, but let's do the most obvious way. Let's say we got 1 here, 2 here, and also 3 here. That's the order. That means we're going to handle expression followed by term followed by factor. Okay? Somehow, this order here turns out to be quite work-saving for us. I'll point out something here that's more like an insight, which you may not grasp right away, but you will see that, maybe once you do the exercise yourself. Okay, one thing here, right? Remember when we want to do this replacement here, right? It's about indirect. We only do that if the current variable produces another variable, right? So now let's say this. When we are handling number 1 here, there's no other variable that comes before that, so nothing for us to consider. But when we are considering in the second iteration, this term over here, but this term produces another variable, factor. However, factor comes after term. That one doesn't really fit into this definition here. Okay? Just keep that in mind. Okay? You will see that. Okay? And also similarly for factor as well. My point is somehow by choosing different order, maybe the amount of work you're going to do could be a little bit different. But I would say overall, you should just be able to result in the same kind of grammar without any left recursion. So that's the bottom line. Okay? For that insight, you can think about it maybe a little bit later. But let's just get to the tracing, so you just definitely get an idea. So the most important thing to sort out is, once we get the order for the variables, let's now make sure we understand about this pattern over here. Okay? We're just going to follow this pattern here faithfully. And the n here, it's just about how many variables we have, right? We got 1, 2, all the way to n. So we got 1, 2, all the way to n. So n will be 3. All right? So let's now just try to map out all the possible combinations of I and j. Okay? So for this part here, okay, I'm going to put it here. So we got I here, and also we got j here as well. Let's see the combination. I apparently can be 1, can be 2, can be 3. Right? The outer loop has only 3 iterations. That one's obvious. And for the inner loop, we say that j can be 1 all the way to I minus 1. All right? When I is equal to 1, we are saying that j is going to be from 1 until 1 minus 1. We're basically talking about 1 dot dot 0. What is this? Is there any interval? Well, does this interval here contain any value for us to look at? From 1 to 0? Not really. This one is more like an empty interval, conceptually. All right? That's something you want to keep in mind. All right? So here, I'm just going to write down. So this is like a special case. So j over here will be nothing. Because 1, 0 is empty interval. All right, it's a very important, but very subtle, but that's something you want to just remember. Right? Of course, if you write this in the for loop syntax or while loop syntax in Java, you can also easily see that when I is equal to 1, there's simply not any work for us to do because there's no variable that will come before index 1. Okay? But for 2, only 1 will come before that. And for 3, both 1 and 2 will come before that. We'll see. All right? Okay, what about when I is equal to 2? In that way, we should really go from 1 until 2 minus 1, which will be 1. Right? So here, we only got to consider 1 for j. What about when I is equal to 3? So we should really consider j being 1 all the way to 3 minus 1, which will be 2. So 1 and 2. First of all, this is a pattern that we should know, right? Maybe even from first year, second year courses when you talk about nested loop, right? That one should be not a problem for you. But let's see how this pattern here can be interpreted on the grammar that we have, right? Given that the indices we have, right? You can think about the 1, 2, 3, 1, 2 over here correspond to the order we just imposed accordingly, right? So let's now make some additional annotation. So 1 here really represent expression. And the 2 over here really represent the turn. And the 1 here, again, represent expression. Okay, I'll give you some further interpretation in a moment. So 3 here really represent factor. And 1 here, again, represent expression. And also the turn. Right? Of course, if you choose a different order, for example, you might choose maybe 1, 2, and 3 or whatever, right? There are different combinations you can choose. That's completely okay, but just that the interpretation here will be a little bit different. So that means the work you're gonna do will be also different. But that's okay. It will still end up being working, just different, okay? So now what does that mean? That means when we do, for example, expression here, well, there's simply nothing for us to do, which is good. Nothing, right? However, here, let's say turn and also expression, right? You can think about I and J. Do we have, so when we say AI and AJ, this should be a production from AI to AJ. Do we have a production from turn to expression? We don't. We only got expression to turn, but we don't really have turn to expression. So the way, that's kind of the insight I just mentioned right in the beginning. The way we choose the order somehow saves us some work. Simply because we don't really have anything like a turn produces expression, or factor produces turn, or factor produces expression. There is no preemptive replacement we have to do for phase number 1 completely, it turns out. Right? That's an insight you may want to think a little bit more about. Right? I just want to mention to you. It's also recorded. You can also think about it. All right, let's now run the algorithm very quickly. Right? So in overall, we're going to get how many iterations? So because every combination of I and J will correspond to a certain step we've got to do. Right? So 1 step, 2, and also 3. Right? So 3 things that we're going to look at. Well, let's look at one by one. Okay, so this one here, we already know we don't need to do anything. We just skip, right? So now let's talk about different combination. So let's say when I and J, let's say I is equal to 1, beg your pardon, I is equal to 2, right? I'm talking about 2 and 1. And J is equal to 1. Let's see this one here, right? So that's exactly this one here we're talking about, or just color that. This one here, oh, you know what? Let me use maybe this one here. This one here, and then we got 2 and 1, right? That's the first combination. You know what? Let me make it a little bit darker. 2 and 1, and this one here. All right, the first one here. Now, for each one of them, we got to talk about, first of all, phase number 1. Phase number 1. Do we have any AI to AJ? Phase number 1. Do we have any AI to AJ? Meaning that, do we have AI is really corresponding to turn? Produces AJ, which will be expression. Is that a valid rule? No, because we don't have anything about turn produces expression, right? You can see turn only produces itself or factor. So we are safe. Nothing to do. All right? So this one here, do nothing. No. Luckily, the way we choose the order, like 1, 2, 3 over here, phase number 1 is completely do nothing for us, only for this example and the particular way of ordering. So I'll put down some exercise right away. You guys may actually want to try some exercise to try different order of the variables. Okay? Reorder variables and re-execute the algorithm. Right, some exercise you can try. Apparently, there could be different, maybe several possibilities. You can just choose one of them, just to give a try. All right, phase number 1 is not going to work. How about phase number 2? Phase number 2 here is going to be the interesting bit. All right, phase number 2. All right. So for phase number 2 here, we're saying that AI, which is the turn, right? I is actually now 2. So we are saying turn. Do we have any left recursion identified for turn? Yes, we do. Turn produces turn, right? I'll put it here. So according to this rule over here, do we have any AI produces AI instance? Yes, we do. We basically talking about I is turn. Do we have any turn produces turn? Yes. So there is something for us to do. You can think about for every occurrence of like this, we're going to replace it by the pattern we explained before the break, right? And to really help you execute this pattern over here, let's now try to see what we can do. All right. So for phase number 2, the way to do it is, let me just expand this to make this complete, right? So what we get is we got turn produces turn multiply factor. Multiply factor. Okay, right here, right? That's a left recursion. And the way to, okay, let's now try to do this together, right? AI, turn. AI, turn. The rest will be alpha. There is also gamma, so there's also beta, which will be just a factor, right? The alternative, all right? So let's see, or factor. Let's now try to find the correspondence, and then we will be ready to turn that into the right recursive version. That's correct, all right? First of all, let's identify them. So you can think about this one here is AI. This one here is also AI. This one here, starting from the multiply, basically the rest, right? This will be the alpha. And this one here will be the beta. All right? And just a quick reminder, before the break, we kind of argue that this pattern here is just going to be basically beta followed by 0 or more alpha. And to really produce this exact pattern without a left recursion, that's the grammar we need. That's going to be right recursive, all right? So the way to do it is like this, okay? So I'm going to write down the solution here, but you guys can see the correspondence also, okay? So here for phase number 2, okay? So what we have is turn produces, I'll also annotate correspondence in a moment. Factor, and then followed by turn prime. That's the new variable we introduced, the prime, okay? And then we say turn prime produces multiply, and then factor, followed by turn prime. All right, let's now, also epsilon, right? Don't forget, the epsilon actually, it is important because we say 0 or more occurrences. Epsilon over here. Okay, let's annotate quickly. So you can see that over here, this turn over here is the AI. This is the AI. And then this one here is the beta. Beta. And also we got turn prime. AI prime. And then, of course, this is AI prime. And epsilon, epsilon. And then this part over here is the beta. Right? Alpha, I beg your pardon. because you can see this is the alpha right here. Okay, I just said it wrong. It should be alpha, not beta. Beta is right here. Okay, and then the term prime, which is AI prime, right recursive. So we replace this particular rule by this. Okay? So this will be done right here. And then if you go for the next iteration, so basically we are asking whether we got factor here. Phase number one, we re-argued, this will be something you can also write down yourself. Phase number one, we have no work to do. Do we have factor produce this expression? We don't. We got some parentheses over here. Also, do we have factor produce this term? Also, we don't have it, right? So there's no work to be done for phase number one. How about phase number two? Do we have any left recursion anymore? Do we? So here we talk about factor. Do we have any left recursion here? No, we don't. So we're done. Okay? All right, question here. Yeah.
Why didn't we do phase 2 for I1, K1?
Sorry, say it again. Sorry.
So why didn't we use phase 2 for the case where I is equal to 1 and J is equal to 1?
You mean I is equal to 1, j is equal to 1?
Yeah, so wouldn't we have to check, because the expression is giving us expression for plus term, right?
You're actually right. So that's something I just missed. Thank you so much. I think you're right. Okay, so guys, I think your fallacy was exactly right. Okay, right. So notice that this part over here only applies to, okay. Yeah, you're right. So this part over here is really, okay, so this part over here, nothing to do when I is equal to 1. Because in that way, we got empty range over here for phase number one. Good. And then this guy here, which I'm going to highlight, I think your fellows did again, he's absolutely right. So this one here is really using AI and AI, so which would be 1 over here, right? In that way, we are able to identify the left recursion right here, because we're going to remove this left recursion as well, which we haven't. Very good. Good. Okay, I'm going to write it down here. Okay, so we should really do another one, which will be when I is equal to 1. Okay. Phase number 1, not applicable. Because this range over here is empty, right? But phase number 2 will identify the expression produces expression exactly here. And what should we do? We just do the same replacement that I just showed to you. So overall, for this particular exercise over here, there will be 2 replacements we have to do. Number 1, when I is equal to 1, we're going to replace the left recursion right here by this pattern over here. And then number 2, when we get to when I is equal to 2, we also need to replace this one here by that pattern there. So 2 patterns. All right. So this will be some exercise for you. You can definitely write it down. So the exercise to do the replacement. Phase number 2. All right, something for you to do. All right, any question about this one? Okay.
Yeah, I have a question.
Yeah, go ahead, please.
In phase sorry, phase 1, but when I is 2.
Mhm.
So we checked, do we have term becoming expression?
Yes.
You said no. How come we don't check term becoming factor, since term and factor?
Very good. Very good question. Let me repeat your fellow student question, which is completely valid. Apparently, over here, we're only checking if there's any term produces expression. Apparently, term produces expression doesn't exist in the grammar. That's why I said nothing to do. Why are we not checking term produces factor? I'll write it down explicitly. Before I answer, anybody? Again, let me say the question once more, okay? That's very important. That really has to do with the insight into the algorithm. I think this might be the last bit we'll go over. We can do another exercise maybe on Thursday, okay? So this one here, let me repeat the question again. So according to the pattern over here, we say that we check to see whether term produces expression is a valid rule. Term produces term, well, term produces a factor. So we don't need to check it. There's no such rule. However, why do we not have to worry anything about term produces factor so we can do the replacement? Why not? Yuri?
Is it because it won't result in a loop? Because only the ones that the rules we've already gone through?
That's basically right. Or more precisely, since we already decided the order is 1, 2, and 3, right? So if you think about here, the term has the order of 2. I have the 2. And the factor has the order of 3, right? So here, remember, so here you're basically saying if something that comes earlier produces something that's later. That's not the way to go. We only try to see if something here produces something that's earlier. If no, then we don't need to worry. That's how we break the cycle. Okay, good. So this one just requires a little bit more insight about how you can consistently apply the rule. Okay. And of course, if you choose a different ordering, you may actually have to do a little bit more replacement for phase number 1. But as I said, after all the work you do, it will still end up being the same grammar. That's equivalent. All right, guys, any questions? Okay, we only got about 1 minute left. I don't think it will be enough for us to do the second exercise, but I would encourage you guys to try definitely 1B over here. That's just about another left recursive grammar that you can see how to remove it. And then for 2A, that's something I'll do in the beginning of Thursday, very quickly. That one just about how we can break the cycle by doing replacement, just another like a phase number 1. We can do that, but if you want to try it out yourself, feel free. But definitely you're going to assign 2B and 2C as exercise for you. And then we'll talk briefly about eliminating epsilon production. And then we'll move on to talk about something about backtrack and also the first set. That's really important to understand about the top-down parsing. Yeah.
Sorry, back to where we were. When we were doing phase 1 for I is equal to 3, we check, does AI ever turn to AJ? So we have to check, does factor ever turn into term, which we said is no.
No, yeah. Also, does a factor ever turn to expression? Also no.
But we have factor turns into bracket expression. Is that different?
That's different. Another good question, right? So here we talk about literal. Does factor produces expression directly? But here, this is parenthesis. That's blocking it.
Because it's the first thing.
Again, so guys, your fellow student question again is very valid. So here, A and AJ. AJ here got to be AJ directly. But here, we actually got AJ, but that's preceded with some symbol. That doesn't match the pattern. Okay, another very good question. Thank you so much, and then I'll see you guys on Thursday. Okay, thank you.